Welcome back. Let's see. Number one, just to be sure that you have all the information that you need. Remember, you have the homework. For your homework, something that is important. This is the first homework in which I am asking you for source code. It is not a paper as the previous ones. I am not asking you just for a paper in which you explain some things. I am asking you for the real source code. We want to run your source code and check that you are really working in programming, right? So important thing here, you need to submit source code. Now, I am asking you for the source code of two different things. Number one, I am asking you for source code to train a model. One source code, hopefully one program, one class, separate from the others, is going to have access to a data set. I am asking you to access a data set that is different from the one that I have shown to you. Either your data is a CSV file, or you are using something from the USC dataset repository, or your own data about something. The IRIS dataset is used 150 data, so you can imagine that, well, you can use something that you have. I could use the grades, your grades, well, not your, but the other class, 200 students, and figure out if some model can be created. I am asking you for your data, something that you're familiar with or something that you can research. I am asking you to create a model. Create a model, basically, so far, you know, figure out the parameters, search for good parameters, create a model that is good enough to be deployed. That program is going to be very similar to the ones that we have reviewed here, because basically the architecture that you're going to follow is very simple, similar to the others. But this new data, new parameters, figure out things. Second, the most important part, the new part, I am asking you to create an application. An application in which you get the model that you created before, hopefully you save, and then you can load. And this application, my goal for you is ask the user for some data. Remember that I showed you the example with the IRIS data set. Ask the user for 4 numbers for the input, put that input in the model, make the model to predict something, whatever you are working on, and show the result to the user. Obviously, you are going to be the user, the TA is going to be the user, I am going to be the user. My goal is for you to notice the difference between, okay, you do the training and the percentage, oh, it's a wonderful 95% perfection, and then come the human and you're using the model, and it is not true that 95% of the time that you use it is going to work perfectly, and you're going to notice some problems, issues. Reality versus statistics. That is my goal, but obviously for you to practice programming. Now, your submission. The most important part of your submission, Java files. I am expecting you to submit your Java files. Now, there is going to be a TA grading your work. It could be very nice. Hopefully you can do it. You can also submit a jar file with your project build, or if you need to explain something in order for your project to be run or executed or compiled, if you're using a library to plot something or to make some graphics, I don't know, could be a good idea to put a README file so you can tell the TA, hey, you need to do X, Y, or Z to run my program, because it's something that she's going to be doing. So be nice. Remember, it's a human being grading your work. So tell that person what that person needs to know. That is your homework for. Moreover, remember, you can work individually if you want, fine, or you can work in a team of 2 or a team of 3. That is the top 3, no more than 3, in order to do your work. Again, if you are 3, my expectation is 1 person can work in the training and the other 2 or 1 to the application. And well, you have 1 element that can, I don't know, go for the pizza. Help. So 3, 2, or 1, and your goal is to create source code. Finally, I am not asking you yet to work with the convolutional neural networks. That is going to be something that I am going to start doing today. That is going to be your next homework. So I am asking you to work with something simple. Again, trivial data. You can use images. You can work with something similar to the numbers. Small images, easy to identify, mostly black and white, and still a neural net, small one can work, kind of. So don't worry a lot for the complexity of the data set. So far, I am aware, and even I recommend you to use data sets that are easy classification models, because for images and other video and things more complicated, we need to introduce the convolutional part. And I need to be sure that everyone is aware of that. Yes?
Sir, in the assignment, you said we have to use a new data set. But are we allowed to use an iris or an LMS? Do we have this?
Use a data set that we haven't mentioned here. So use any data set except the MNIS, the numbers, and the iris. So except those two are the only ones that I have used so far, if I remember. So except of those, any other that you want. There are some data sets that are comma-separated values. You can use your own data. If you have data for some project, you can put your data to work and see what happened. If you do that, just remember the TA will need the data, so because he's going to run the training part. You'll be aware of that. Good? Clear? Okay, so next, yes.
It might take more than half an hour. So,
What?
so for training the data set, it might take more than half an hour. Is it fine?
It is fine. I can let your program run for 1 day or something. I am hopefully it's not more than 1 day. I don't know. Well, you tell me. If that is going to be the case, again, be nice with the TA, and if you can include a README file like, hey, this is going to take 5 hours, 6 hours. I mean, again, just for her to be aware that something is going to be running there. Please help, right? Good. Okay. Again, the idea is that you familiarize with the process. My request for you: try to make a model that achieves this good performance, 0.05. I understand that for some data sets, even if you tried your best, that is not going to be possible. If you are close to that 0.05, the closer the better, right? But again, do not move to convolutional. Do your best. And I understand that some data is not going to perform good with use this neural network without the convolutional part. So I am okay with that. But if you have a particular question, send me an email and I can talk with you about particularities of your data, your model, and try to figure out ways to improve if there is any. If not, I am going to just allow you to, okay, that is the result, that's it. Clear? Okay, we need to finish with neural networks because that is the last thing that I am going to include in your midterm. Remember, spring break, and after spring break, my goal is to start talking about a review and your exam. So something that we need to cover regarding neural networks is the convolutional part. I want to be sure that everyone is aware of that part. Something that could happen, guys. I need to finish with the concepts, but also I need to finish with the implementation. Something that I think could happen is that I am not going to be able to finish everything today. So worst case scenario, even though I mentioned that after spring break, the first class we have a review and the second class we have the exam. So the exam was planned like the second day of the week. Something that I think is going to happen is I am not going to finish today. I don't know. And therefore I finish in our next class and the review the second day of the week. And then the exam could be moving to March 22. Hopefully that is not a problem. So I think that is going to happen. March 22, the exam. And obviously include everything that we cover and we review the class before. Okay? Okay, starting. Something that we have done so far with the neural network is that images, in particular, video, Video is just a collection of images, frames per second, images in a second that we need to process. So at the end, we have a small problem with pictures because yes, the model that I show you were these pictures 28 by 28, and that gives us this input of 748, right? Okay, for this thing, that looks fine. However, just imagine what could happen if you use exactly the same model or the same process for a picture that is 300 by 300. And still that one is small. But you can imagine what could happen in a real picture of 1000 something by 1000 something that is kind of a good resolution. The issue, number one, is going to be that we need a lot of neurons for the input. And if we have at least one hidden layer, remember that all these are connected with all these. So the number of connections is going to be crazy a lot. And obviously, problem number one is that crazy number of connections is a crazy number of W's, and it's a crazy numbers of calculations that we need to know. Because again, the problem is not the lines that we have there. The problem is each line corresponds to a value that we need to calculate and update several times. Problem number one. Size, memory, performance, whatever. But the most important part of the problem is problem number two. Problem number two. What we did is to take this picture that was 2D. And step number one, all the pixels are inputs. So basically you take something that is 2D and put flat. And flat for inputs. Yeah, very simple. There is a small problem. When you take something that is 2D and just make this a line, you are missing information. What kind of information? Yes. Imagine that you are searching for a line. You are searching for a square or whatever. If these three are the same value, it's because there is a line there. But when you put the data flat, instead of having, for instance, 0, 0, 0, 0, 0, 0, and these 3, 1, 1, 1, which give you the idea of something dark here, something white there, you transform that thing and use this. And automatically you lost the relationship between the different elements. I am talking about the relationship, the space relationship, the connection between them. And that is something that is not a good idea when you are trying to recognize objects. It doesn't matter that it's just a line or a cat or a dog or a signal or letters, whatever. Hopefully we can agree that there is a value in the pixel itself, but also the pixels around. Not all the pixels in the picture, but for me, whatever I have around, somehow it is important for knowing I am part of what? Use the environment or the cat or the dog or the signal or the letter or whatever. The memory and the relationship between the elements are the two reasons because we're going to move from the models that you know to something else. Something that uses less memory, that is important, but the most important is something that gives us the opportunity to preserve the relationship between the things that are around. Clear? Okay, the tool that we're going to use for that is a tool that is a mathematical tool. Yeah. this idea of convolution. Convolution. Let me explain you the big picture, and then we need to review the elements one by one. The big picture, the one that you're going to look to any textbook or any place when you search for this concept of convolutional networks, or convolutional neural networks, is going to be the idea that, you know what? When you have a piece of information, again, audio, video, pictures. In particular, this is useful for the video and the pictures. Again, the video is pictures. Instead of reviewing the full picture with the neural net, the key idea here is we are not going to review the full picture. We are going to review small parts of the picture. What does it mean that? That instead of using as an input all of this, we're going to be using somehow small parts there. Obviously, we're going to move this window, and in some point, somehow, we're going to review everything, but use one space at a time. Think about this. If I take a picture of this classroom, what you do, what your brain do, is you're not looking here at the center, even though you have the capability of looking all this information. That do not happen. What you do is look here, 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 scanning, right? They apply the same concept to this thing, making them smarter. We have the picture, and we're going to analyze one part of the data at a time. What is the analysis that we're going to do, and how are we going to put things together? I am going to explain, don't worry. The only thing is, the main idea is moving with small parts of information. Now, doing that is going to allow us to reduce the use of memory. Why? Because at the end, remember, what I am doing is something with linear algebra, something with matrix multiplication. It is easier or require less resources to do a matrix multiplication of this size several times instead of thinking about the full classroom as a matrix 1000 by 1000. Split, divide and conquer. That is what we're going to do. Okay, how we're going to implement it is a different story, but that is the implementation. Now, something that is going to happen is we're going to review the original step by step, small squares. And when we do that, we are going to create a representation, a matrix, that is equivalent to the original one, but not the original one. Something is going to happen there. Again, I am going to explain. What we are going to do is this process of small parts, one time, another time, another time, another time. How many times? How many convolutions you want to do? That is going to be another factor for your architecture when you create a neural net. It's not going to be only the number of layers and all the parameters that we have reviewed, but now is you're going to do this idea of analyzing something in parts. Good. How many times are you going to do that? Don't worry, I am going to explain you that. Use to check with the picture. Now, you know what? You are going to apply this process, the parts, several times, as many times as you need. But in some point, you are going to go back to the models that we reviewed. In some point, when you finish with this selection of small parts, small parts, small parts, small parts, you are going to take the full thing that we have as the input to a neural net that is basically exactly like the one that we had before. What I am telling you is you are going to notice that your new version of neural nets is going to be with something that we're going to call a convolutional layer, a layer in which this thing is going to happen. You are going to have several of them. But in some point, you are going to go back to the two that we used before. The hidden layer, the layer in the middle, the dense one, and one output layer. The only thing that is going to happen is now we're going to add a new type of layer. A new type of layer to do this thing convolution. This thing convolution related with this idea of reviewing the input, not all together, but in parts. Makes sense? What is going to happen here and the details about how to split things, next step. But this is big picture. We still need what you are doing right now, and we're going to add more things. What does it mean that we still need this? That all the things that you review with softmax, the things that you have with negative logarithm likelihood, the things that you have with the initialization of the weights, etc., still is needed. But more things are needed also. Good? Okay, next. We need to review the details. Let's see. Number one, convolution. Convolutional layers. They are called convolutional layers because they are going to do one thing that we call convolution. And let me be clear, that is a mathematical operation. Convolutional neural networks have convolutional layer, and this convolution thing is a math operation. A mathematical operation, really? A mathematical operation that is going to look something like the following. You have a picture. In your picture, select a part of the picture. This guy here is one corner in the picture, or this guy here, or this guy here, whatever, one space, maybe one face of you in the picture of this classroom. That part, I am going to represent it with these squares. Now, I am going to use the case in which the picture is black and white, so I am using zeros and ones. But if you have a color, RGB, right? 3 values, 3D array. Black and white. This is, again, not the full picture, but one part of the picture. And this guy, what we are going to do is literally take another matrix, another one. And this other one, I have this one, and I am going to take another one. Another one that is usually small, 5 by 5, 3 by 3, 2 by 2, small things. And what I am going to do is to take this one and do the following operation. And hopefully you can more or less make sense of what is happening. Imagine that you take this one, always it's going to be smaller than this one, and put this rectangle here. And when you put the rectangle there, make a multiplication. Hopefully you notice that if you put this one here, the one in black with the one in white, 1. The one in black, in white with the 0 black, 0. The one here with the one there, 1. 0, 1, 0, 1, 0, 0, 1. How many ones do I have? Multiplication, addition. If you agree with me, we get 4 ones. If we do the addition, 4. The result, another array with that number 4. Okay, next step. You did the multiplication and addition of this guy, like with this. What if now we move that guy, and instead of covering this here, we cover this here? So it's no longer this one, it's this one, this one, and this one. And do exactly the same. 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1. Everything that has a 0 is going to be 0. Only 1 and 1 are going to survive. And then I am going to do the addition. And hopefully my maths are correct. And I got 3 ones. And then this one, again, was here. Then here, now here. And the same operation. Multiply and add. I am explaining this like a programming, right? This. But you can put this as an equation. And if you put this as an equation, basically what you have is this one here that are my inputs. Multiplication with this that are W's, 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 and continue. And then addition and discontinue. And I am sure that this equation start looking familiar. W's times X at. Looks like something that before a neuron was doing. Input, constant. The same. Now, 1, 2, 3, and now go back, go down. 1, 2, 3, go down. 1, 2, 3, and the result is something like this. Again, it's not the full picture, it's one part of the picture, and this is just new values, new W's. Tell me, what do we do with the W's? Step number 1, with your W's. What are the values of the W's at the beginning? Random numbers. So if you're thinking about what are going to be the values here, at the beginning, random numbers. What is the goal of multiplying random numbers, the input data? Creating an output. And then you review if the output is good or not. And then back propagation. As bad as the output was, calculate the gradient, the derivative. And do you remember that basically what you do is your new W is going to be equal to the old W and some operation with the gradient. Are we going to do this with these W's? Yes. Random. And then go back and we are going to improve them. Did you notice that you are doing exactly the same thing that we did before with the neurons, but now the W's are 2D and the input is still 2D. We're playing with this idea of keeping the 2Ds. Okay, Professor, yes, you are keeping the 2D, but still you are guessing W's values. And how do we know that that W's values that we are trying to guess are going to work? Because of the following. These values here, that at the beginning are random, but that you are going to figure out with the back propagation, that square is called a filter. Filter It's a concept that I am sure you remember or you kind of associate with pictures, images. You work with images, and the images you can apply filters, right? These filters, that they are random at the beginning, but then you are going to figure out, have the capability of modifying any picture as follows. Just to show you some examples. If you get this filter, this matrix, with numbers like this, and you multiply that matrix, all the squares in this picture, all of them, what you get is the same picture but blue. Okay, that is not going to be useful. Okay, but if you change the values and you have something like this, a higher value at the center, negative and zeros around, what you get is a picture in which you increase the sharp. Really, matrix multiplication, the original one with something like this, small, and you have something sharp. This is not a concept of machine learning. This is not a concept of neural network. This is a concept of image processing. The only thing that we are doing is, okay, if in image processing, it is so simple to apply a filter, what if we put these convolutions that is basically, let's start with a random filter and let's figure out if the network can guess these W values that create a good filter. Something that could be more interesting is I want to detect the borders of the picture. These filters detect your borders, horizontal or vertical, with priorities. Something very similar, detect the black borders, borders that are bigger. You are not going to use any of these. Again, a common error. We are not multiplying your input with some filters like this, not even the last one, because we have no idea what filter could work for the problem. What we are going to use as a filter is none of this, but again, random values. And those random values are our W's. And what we're going to do is those random values are going to be changing in every back propagation iteration. We are going to try to figure out a good filter for the image. Make sense? Yeah?
What are we expecting in the output with the filter?
We can visualize the output, and usually it's going to be something crazy like this. But most of the time, it's going to be something like this that eliminate details. But what is going to happen is something like this, expressed like this, is going to be the input for a network like the one that you have. Instead of having as an input the original picture, what you are going to have is as an input for the neural nets, like the one that you are creating, an image that with the other layers, the new ones, have changed in some way because you are using these values to multiply the picture. And multiplying the picture, you are changing the properties of the picture. Usually what is going to happen is this collection of W values are going to help that the input for the network, the normal one, is going to be a better input than the original one. A better input, yes, because remember, so far something that you have with the numbers is, well, I am not clear if this gray have the same value that this black. With all this stuff, something that happened with the numbers is like, this is going to be more clear, more defined. Therefore, this input is going to work better with the model that you already have. You are improving your inputs. How do you improve your inputs? With these multiplications. An issue that you are going to notice, an issue that we have. Yes, we say somehow memory, but Professor, according with the example before, what you are telling me is that now, instead of one multiplication of this by something, what you are going to do is this small place here, small place, is going to have this multiplication 1, 2, 3, 4, 9 times by the filter. Because remember, we move the filter 3 times in a row, 3 rows. The filter is going to run here 9 times. It's a loop of 9. Well, 2 loops, 3 by 3, right? 9 in total. But then you need to consider that this small place, the original input, also need to move horizontal and vertical. So if you think about programming, you have 4 loops, one inside of another. Okay, we are not going to use memory, but the CPU is going to be matrix multiplication like crazy, right? Okay, solution. If you have only one CPU, it's going to be running like crazy. But what happens when you have one instruction inside of 4 loops? That is a perfect scenario for moving to parallel programming. That is a perfect scenario for using multiple CPUs or better, GPUs. Why? It's the same operation multiple times. This operation could become a kernel, and we can put this in as many GPUs as I have available, and therefore they are going to complete the process faster than use this loop. CPU problem solved. Something that you are going to notice. So far, training your neural nets have been easy. I mean, not more than half an hour. Moving to convolutional networks, probably your laptop is going to start having a hard time. Maybe start the heat, right? Because now you are doing a lot more loops than before. Because remember, whatever loops we had before are going to be still there, but we're including more used to pre-process the data to create this convolutional things. Clear. Now, moreover, we can have the original one, we can move the original one, and we're going to have this output that is going to be the numbers that I showed you before. And just for you to remember, this is my input, the image. This is called the filter. The output, the result, is called a feature. The result of multiplication of the image times the filter is going to give you what you call a feature or the feature matrix. You are going to notice the feature matrix do not have the same size as the image. Something changed. Tell me, what is going to be the size of the feature matrix having a filter of 3 by 3? Assuming that we move one column or one row at a time. Rule. If you use this image, section of an image, and the size here is rows in the image, columns in the image. So in this scenario is 5 times 5. And if you have a filter that have rows in the filter, columns in the filter, 3 times 3, your result is always going to be that equation. 5 minus 3 plus 1. Oh, 3. And the columns, 5 minus 3 plus 1. Put more here, or less here, and the equation is going to be still true. you can calculate the size of the feature, knowing the size of the image and the size of the filter. One of the possibilities is that it's going to be a little bit smaller, but it's not exactly a rule. We are not doing reduction, not yet. The only thing that we are doing is to extract characteristics to improve the image, quotation marks. Clear? Okay, now the question is, filters. Random value, right? This equation. What do you think about applying not only one filter, but maybe two? Okay, what about 3, 5, 10, 20? Really? Yeah, one characteristic of the filters in an image is that you can apply a filter and then another. You want to improve the image, and it's not only about sharp or about blur or about something, you can apply several. Instead of working, trying to figure out the values for one matrix, what about trying to figure out the values for 2, 3, 5, 10, 20? Do you think that is a good idea? Yes, it's a good idea. It's a good idea. If one filter do not work, maybe the other, or maybe the two together are better than one. What does that mean? That means that you're going to have a matrix that is the image, and you are going to multiply this guy for this, and you're going to have a result. But then you're going to multiply that one times this, and you are going to get a result. And this one times another one, and you are going to get another result. You are going to get one feature matrix per filter that you apply all of them using the same section of the input. SAS. Okay, what is going to be the initial value here? The filter. Random. The initial values here, random. The same randoms, they are random. They cannot be the same. If we use 20, we have 20 different versions of random values, and we're playing with all of them. So wait, if this is a picture and each of you is one section of the picture, you are telling me that you are going to multiply him times 20 filters and get 20 results. And then him, 20 filters, the same ones, 20 results, 20, 20, 20, 20, 20. The picture that is a map 2D just become a 3D collection of feature metrics. So 1,000 by 1,000 image just become 1,000, 1,000, but now each section is going to become three-dimensional and probably going to be bigger than the 1,000. A lot of data, right? A lot of data, a lot of opportunities to get good Ws. Moving forward, clear? Good. Now, next thing. You know what? This can become crazy, really crazy. Options to avoid this to become crazy. Let's see. Number one, what I show you is that if you have a filter that is 3 times 3, and this is your picture, you're going to use this, and then you move one here, and then you move one here, you're moving one. That movement have a fancy name, stride. What is that? The number of pixels that you move. In my previous example, you are moving work here, move one, one column. Or when you finish with the row, move down, one line, one. Your stride is one. Can I move or can I use a stride that is bigger than one? Like, can I move instead of from here, one, can I move from here, the gray rectangle, and move to the orange? Move two. Okay, so this one, instead of moving pixel by pixel, is going to move 2 pixels by 2 pixels. What do you think could be better? 1 by 1 or 2 by 2? Stride 1 or stride 2? Always, always, always. Well, not always, but 1 by 1 sounds like the best scenario, cover everything. However, what happens when you change this from 1 to 2? You're reducing half the work. I mean, just moving the jump from 1 to 2, you're saving a lot of calculations. In which scenarios moving 2 could be almost the same as moving 1? In pictures that have low number of details. Think about the numbers. If you have a picture with this number, really make a change 1 by 1, 2 by 2? Probably, well, in this one, no. The lines are going to be still lines, 2 pixels above. Obviously, if you are working with the picture with the cat or the dog or something with more details, probably in that scenario, you want to work 1 by 1. It is a decision that you are going to make when creating the architecture of the neural net, the strides. Why I put this in one slide with the title at the top? Because remember, we are reviewing concepts, but later we apply the concept using a library. And in the library, there are going to be parameters, and the parameters are going to have these fancy names. So you can imagine that later in the library, in some place, you are going to be asked about the stride that you want to use. Or you are going to notice a number 1 or 2 stride. And I need you to know what is happening there. Click. Again, this is a color picture. The numbers are not zeros or ones, but you have a filter, you do the multiplication, you do the addition, and then the result is going to be numbers that are bigger than just units. Same process. Now, another concept that we need to consider. Did you notice a problem with this method that we are following? A problem that you can notice is, tell me, how many times this number 1 is going to be used? Or how many times this number 77 is going to be used? How many times this number 44 is going to be used? I don't know if you notice the rectangles in different colors, green, red, so on. But my point is, these guys, but this guy, more than 1 for sure. I mean, you can do the counting, but it's like the things at the center are going to be used in a lot of equations, but the things in the borders is like one time when you cover that part, right? There is any way to increase the number of times that you use the elements in the borders, particularly the first column, the first row, the last column, the borders? That one, something like this. We can add columns. Now, remember, we are talking about this small part of the image, but this small part of the image is the green part. The things in gray do not exist, are not part of the image. But instead of putting this small part alone and do these filters applications, I am going to put this part inside of something like this. Why? The only reason, because now the values in the borders are not any longer values at the border. Yes, still the things at the center are used the most, which is okay, because if you think about looking to something, your attention, your brain is more into the center. The peripheria is not something that you pay attention. So somehow the neural net is working in the same way that your brain, quotation marks. But at least you increase a little bit the number of times that you work with some of the values into the borders. This thing have a name, a fancy name. So when you're creating a model, you're going to be asked about the padding number that you want to use. And can we agree that this picture is showing a padding equal 1? And what if I ask you, what does it mean padding equal 2? Or padding equal 3? We are clear, right? Okay, padding to avoid this problem. Good. So you apply padding, you define your strides, and you do your equation. And at the end, if you put all these things together, your image, multiply by a filter, and you have an output. And this one can have padding or not. This one can move 1 by 1, 2 by 2, whatever, you define your stride. This is the process of convolution. Important concept, the filter, the padding, and the stride. Good? Good news, you do not need to do the multiplication by hand. The library is going to take care of that. Good news, you are not doing the back propagation by hand. The library is taking care of the back propagation, and in the same back propagation that other W's are calculated, the W's in the filters are going to be calculated. This is the first step, the convolution. Now, we have a problem, or better, something that happens when you apply filters is you are missing the original shape of the picture. And you are missing some parts, but you are highlighting other parts. And you know what? The parts that you are highlighting are more important than the parts that you are missing. And that opened the door to do the second part of the process. Imagine that this here was the result of the convolution. Imagine that you have your picture and you multiply by your filter and you get this feature matrix, and this is your feature matrix. So this is no longer the picture, this is not the filter, this is the result of the multiplication, right? And you have something like this. And you can notice that you have these value zeros, these 2, this 30 here. And these are pixels, remember? So you have these pixels black, almost black, and this one is kind of the important one in this part. Similar thing here, or here, or here. Something that we can do to reduce the size of the picture, literally, to reduce the size. Because remember, we want to do this with a small number of inputs. After you do the convolution, usually the next thing to do is to eliminate data that is not helping us, data that we consider garbage or extra. And one easy way to do that is the following. Pooling. Pooling. What do we do? Take your feature matrix and put together pixels in columns and rows. Imagine divide your image not in one pixel, but in group of pixels. We can do pooling. Can you understand what does it mean pooling 1 times 1, 2 times 2, 3 times 2. If I told you that this one is 2 times 2, take your feature matrix and put together 1 pixel per column. Obviously, this is the original, the picture. So you are not going to use this. No pulling at all. 2 by 2. Put together 2 pixels in the same row and down in the same column. 3 by 3. Put together 3 pixels or 4 pixels. Always is going to be keeping the proportions. And step 1 is to put them together. I put here different colors, right? So this is one group, another group, another group, another group. Remember, it's not a picture, it's a feature matrix. You put them together, and then we're going to have something called pooling, and you can select your number, but then there is something called max pooling. Max pooling, yes. Do your pooling 2 times 2, and from the groups that you create, give me the maximum number, max pooling. And the result is going to be that from this group here, the maximum is the 20. From this group here, 30. From this group here, and finally from this group here, 37, sorry. 37. So that is what I have. Reduction of the picture. Clear. Okay, Professor, do we always do the max pooling? What do you think about an average pooling? I like the idea. Add all the values divided by 4 in this case. What about sum pooling? Do not divide by the total. Guys, for images, which of those 3 could be the best? Depending on what you are doing, one of them is going to work in general. And this is kind of a global sentence. The one that you're going to look the most is the max. Because usually the solution that works for most of the problems, not all of them, but for most of them is if I keep the maximum value, that is the value that really make a difference with the rest of the picture. If you're thinking about face recognition, those values with the max value are going to be related with your eyes, your nose, your mouth. And those are the things that we need to identify a face. So max is going to be this kind of idea of you already identify the lines, the stripes. And with the max, it's going to be like increase the contrast in those lines. And then you're going to pass that to the neural network, because remember, this is just convolution and so on, is to improve the input. But we still need to do the work of the last layers. Good. Okay, usually, not mandatory, but something that is common for the architecture of convolutional neural network is the following. You put a layer that do the convolution, and it's a good idea after that one to put a layer to do the pooling. And what if I want to do another convolution? You can do it. And usually it's going to be followed by another pooling layer. The architecture that you're going to have in a convolutional neural network is going to be something like convolution, that is this filter application, reduce. Another convolution, another filter application, reduce. And again, and again, and again, and again, and again. And when you're happy, you have a 2D array of numbers. And that 2D array of numbers is going to be the input for a neural network, just like the one that we used previously. Please. Yeah, okay. Now, if that is clear, and we understand that the process is going to be something like this, again, this is the one that you already used, and all the above is just playing with the picture. Convolution, reduce, convolution, reduce, convolution, reduce. As you notice, the convolution do not increase the size of the image. Because remember, the convolution, the image, the filter, and your output is always going to be input minus filter plus 1. And the filter is always greater than 1. So always the convolution reduce a little bit, almost nothing, but a little bit. However, if you apply this pooling after each convolution, something that you are going to notice is a big picture, reduce, 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 always, always, always. What you have at the end after all this is going to be something smaller in terms of an array than the original input, always. Guys, the only thing that you are doing is to reduce the size of the input in a smart way. Because every time that you reduce something, what you are trying to keep is the good features of the image. Good? And when you're happy with your reduction, that is your input. Now, how many times do you think it's a good idea to apply convolution and reduction? 1 time, 2 times, 3 times, 20 times? For a picture like the numbers, 2 times is okay. 3 if you want. 1 is not enough. Only numbers. For the picture with the cat, to identify a cat versus a dog, how many convolutions? Cat versus dog. Do we understand that the features are a lot similar? It's going to be a lot more than used to. Why? Not because we want to reduce, that is one thing, but also we want to improve the quality, the differentiation between the images. Hey, no, wait, I want to identify cars versus people. Do I need the same number of convolutions, a car versus a person, or a cat versus a dog? And hopefully you agree with me, cat versus dog have a need for more convolutions because more features are common. We need more filters than the car versus the person. The car versus the person is not easy. However, there are features that are very easy to identify. 1 line, 1 rectangle, basically. That is what you are looking for. You are going to notice more or less convolutions. The real challenge creating neural networks is not the neural network per se, it's the architecture. The decisions of how many convolutions, how many layers, how many inputs, and so on, those are the decisions that as an engineer or a data scientist, you need to take. Those are the kind of research that you do, is create a good architecture. And the second part is having a good data. Good? Okay, and I am sure that you're thinking about source code. I mean, all these ideas are kind of, okay, easy, but source code. Source code. The only thing that I need to tell you to create a model is to give you information like this. Identification of the numbers. Guys, for the identification of the numbers, let's move from the neural net that we created before to a convolutional model. And you know what? The convolutional model, people have already played with several different versions of convolutional models for these numbers. And someone decide or someone discovered that an architecture like this one Cool work. Can you explain to me what those numbers mean? 5 by 5, what? Filter size. 20 what? 20 filters. Can you imagine this 3D array, 20 and 5 by 5 each, and each of them is a different filter, 20 different filters. Okay, that for one of the layers. And then max pooling. Remember convolution, pooling. I want a second layer, a second convolutional layer. Now 50, 5 by 5. You're going to apply more filters the second time? Yes, because I have a better image. Another max pooling. And then a fully connected layer, a dense layer, and an output layer. By the way, for the output layer, I am still trying to figure out numbers. I am still trying to figure out probabilities. I am going to still using negative log likelihood, and I am going to still use softmax. And the source code. Source code. If I give you this source code, do we understand what is happening there and connect all this with what I just explained in 1 hour? Let's see. Configuration for the multi-layer. We did this before. Moreover, before we did this one, an output layer. Before we did this one, a dense layer. Remember that I asked for these two? And what about 1, 2, 3, 4? Convolutional? Subsampling layer. Yeah, sorry, they didn't like the pooling. Subsampling. Convolution, subsampling, convolution, subsampling. Help me. Pooling type dot max. Can you imagine other values here besides dot max? Okay. Help me. Convolution, the first one, 5,5. The second one, 5,5. Size of the filter. Can I use bigger or smaller? Yes. What they are going to do? Random values. 5 by 5, 20 new W values that are going to be random at the beginning, and then they are going to change somehow. Stride 1, 1, stride 1, 1. This stride should be something important. It's going to move 1 by 1 with the numbers. Really, with the numbers 1 by 1. Just to show you the example, you can change 2 by 2 and you can check the accuracy of the model. You are going to notice if something changed. Yeah, it's going to change, but not a lot. 1 by 1, by 1, 1. 20 and 50 output. But what is this number 20 there and 50 here? Remember that I asked for 20 filters and 50 filters in the second one? 20 and 50. But you're using the same method output. Yeah, sorry, guys. They decide that the output will be the option. Because what? 20 filters or 50 filters, the output is going to be 20 feature matrix or 50 feature matrix. So that is really the output. But now the output is not just a connection, but this feature thing, 2D things. Activation. They are layers. In particular, convolutional layers. Activation, the activation function, remember? A new one, identity. Remember that we have this equation here. This is the same equation that previously in other layers, we apply a function here. Sigma, the first time. Then we change. Function, identity. What does it mean? Do you remember the identity in a matrix? The function? Identity. In other words, do nothing. Use your equation is going to be your W plus your X for the two convolution. You can use the convolution with some kind of activation function, but usually what you're going to have in the convolution is no function at all. You are just going to apply the filter. Again, you can combine the filter with some kind of activation function. It is not the usual thing. Use the filter, identity as an activation, done. For the output, negative likelihood, we are still with this idea of the probabilities, softmax. And tell me, output, in the output layer, what is the value of this variable here? If this is this data set, this guy is 10, the same 10 outputs that you have before. In fact, these two are the same ones that you had before, but now the only difference is this one have 500 inputs that come from the above. Good news, if you do not put the number of inputs, automatically it's going to take the number from the previous layer. So you don't need to know how many of these are going to have at the end in the last matrix. Something new. All this dot something, you already know it. Something that you're going to notice in this example, this new command, set input type. We're going to tell, or we can tell the neural network, the type of the input. The type of the input, yes, it's going to be a constant. Do we understand what does it mean? Input type dot convolutional flat. Input type, what is this? Java. A class. How do we know that it's a class? What is this? Static or not? Static method that you are calling using the name of the class. Okay, what is going to do this method? It's going to provide a value to tell the neural net that our input is, can we guess what is this 28, 1? The original input, remember? The original picture was picture of 28, 1. What are we doing? We are adding information to this network, telling you, hey, there are things happening, convolutions, filters, outputs, connections, and so on. But let me tell you that the original input, the big one, is 28, and the one black and white. So only one in the C. What happens if it's colors, or if I want them colors? Yes, clear? Guys, if you copy paste this code in the program that you already have for the means data set, run, you do not need anything else to change. The only thing is, remember what was our best case scenario with that data set? The best accuracy that was cheap, because remember that we did several versions. The best one, 90. You can achieve 99 with this. And that is better than any of the options that we create before. Good? No homework, you already have your homework 4. Regarding this, my only recommendation, please practice. We continue with this of the week after spring break. See you, thank you.